Hello, I welcome you all to this another interesting screencast where we are going to be solving this engineering mechanics problem, and it reads the loading acting on a square plate is represented by a parabolic pressure distribution. Determine the magnitude of the resultant force and the coordinates x bar, y bar of the point where the line of action of the force intersects the plate. Also, what are the reactions at the roller B and C and the ball and socket joint A? Neglect the weight of the plate. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We have a plate that is subjected to a parabolic pressure distribution, and the units for this pressure is kilopascals, and this is also equal to kilonewton meters per kilonewton per square meters. Okay, kilonewtons per square meters. That is also what this kilopascals means. We are being asked to determine the magnitude of the resultant force in the coordinates x bar, y bar. That is where the equivalent resultant force will be located on the xy plane. We are also being asked to determine the reaction forces at the roller B and C and the ball and socket at A. Okay, so this is a 3D finding the centroid of 3D. In this case, the only thing we have, of course, is just some pressure which is parabolic in shape. Okay, so I know what comes directly into your mind is computing the volume, right? We need to find total volume for this pressure distribution will give us the resultant force. Later on, we apply the formulas for centroids so that we find the location of this particular resultant force. And then later on, we apply the equations of equilibrium to find the reactions at the ball and socket A as well as the rollers at B and C. So we are still following the same principles. First and foremost, let's draw the free body diagram. So we know that at B, we are going to have, of course, this axis where P is also the Z axis, okay, which represent, so we are saying our P is equal to Z, so we can also say, so Z is equal to P, which is the pressure, right? So the reaction force at B, this is the roller, we only expect one force in the vertical direction, like so, let's call it BZ. The reaction at C, we also just expect one vertical force like that, let's call it CZ. The reaction at the ball and socket joint, okay, we are going to expect three reactions, right? We'll have AZ, okay, then we'll have AX, okay, and then we'll have AY. All right. So now what we need to do now is to compute. We need to find the resultant force by just using a little bit of calculus and then principles of centroids so that we know its location. So before we do that, let's look at the loading and just try to investigate it. When we look at our loading, the loading is symmetrical. It is symmetrical about the ZY plane. Okay, so this plane here, Z, this plane here. When you look at the loading is symmetrical about this plane, right? Agree? Okay, it is symmetrical about that plane. which in fact makes the problem much easier, because where there is symmetry, the problem becomes much easier. And because of this symmetry, then you expect the x-axis, or the x bar, that is the location for the equivalent force along the x-axis to be, we call it x bar, will be equal to 0, okay, or 0 meters. All right, great. So the only change that we just expect is along the y-axis, right? It will just be along the y-axis. Great. So to start with, we are going to get a small section of where we expect the change, and the change takes place along the y-axis. You've seen how the loading is changing. Okay, it's parabolic in shape, is it? Yeah. Okay, and it's been governed by this particular function here. Okay, which is 2 root of y, right? So we need to cut a section. Let's cut a section in the direction where we want. So we are going to cut a section. Since we cut a section, let's say somewhere there. Let me use green. Okay, so let's say we cut a very small section there like this. We cut a section like this. Just imagine we are slicing this part like that, and then we also cut the other side there like that, just cutting a small section. So imagine we have that slice. We cut that small slice there, which looks more or less like it looks more or less like a cuboid, right? So there we go, something like that. Okay, so there we go. So that section is going to have, in fact, is some thickness of some kind. It will have a thickness of dy. Okay, is that so? So we can find the volume for that small cuboid, right? We can find the volume because we know all the dimensions, because from here, from this direction here to there like that. Okay, okay, from here to there, we know that this one there, this is going to be equal to our y caret, which is equal to y. This is the centroid, the location of our small slice. Is that so? Great. And therefore our small volume for that's just a small cuboid, right? Our small volume for that will just be equal to, and then its length, the length of this whole slice is 4 meters, right? And then the height for this, what is the height for this cuboid? I didn't indicate this height. What is the height for this small cuboid? This height is being governed by what function? This height is being governed by the function z, which is equal to p. Okay, so that is, which is equal to p, and then which is equal to the function itself, 2y to the power half. Great. So we have all the properties, all the geometric properties for this small slice. Therefore, a small volume for this small slice is going to be equal to 4 times P or Z times dy. This is our small volume, right? So if we were to expand this by expanding it in this direction, because this is where it is, see? This is where we need to expand this is where the change is taking place along the y-axis. So by expanding it, we mean we sum up all these small slices from the start to the end, that is from 0 to 4. So we are going to use integration, of course. So to sum up all these, then we just need to integrate on both sides. Great. So now we know the formula for finding the y bar, and y bar is equal to integral of the local centroid location for that small slice times dv divided by the total volume, which in our case is the loading. Okay, so can I move this? All right, okay, it's fine, because I feel like I'm running out of space. Okay, there we go. All right, so now with that, then we just need to replace. So we have y bar is going to be equal to integral, we are integrating along the y-axis, so from 0 to 4. Y bar, we said y caret bar is just y, and the dv we already defined it as 4p, then we have a dy, and then divided by from 0 to 4 there, then we have just a 4p 4p dy. Great. Let me use the space underneath this side. I'm coming this side now. So now let's continue. So we have y bar is equal to integral from 0 to 4. We have y, then there we have a 4 by 2y to the power half dy divided by integral from 0 to 4 4 by 2y to the power half dy. And then when we write this, we can factor out 8 outside to the power 4. Then we have y to the power 3 over 2 dy. Okay. Then divided by, we factor out 8 also. So y to just the power half dy. And if we integrated this, then we'll find that we are going to find that of course 8 and 8 cancels out. Don't forget the total volume. If we integrated that, then we'll have y to the power 5 over 2, then 2 divided by 5, evaluating this from 0 to 4, divided by y to the power 3 over 2, 2 divided by 3, evaluating this from 0 to 4. Then eventually this gives us a 2 times 32, right, divided by 5 divided by a 2 by 8 divided by 3. So this eventually is going to be equal to 2.4. Great. Okay. So our y bar is equal to 2.4 meters. Great. So we found our y bar. We just need to now apply the equations of equilibrium. So we know where the equivalent force is. If it was somewhere here, you know where it is. It's 2.4 from the reference. So if we are to draw this, let's indicate it here. So imagine maybe it is somewhere there. Just 1 minute, I just move this. So this is CZ. So imagine our equivalent force was somewhere here. It was somewhere here. Okay. So imagine this is our equivalent force. So imagine this is our equivalent force, which is equal to, I'll show it, but its position from there to there is, its position from there to there, use blue. Its position is 2.4 meters in the y-axis. Okay. And then we said the force itself, integral from 0 to 4 of dv. Mind you, we had cancelled out the 8 there, so the 8 will be there like that, then times 16 over 3. This one here, you see this one at the bottom. Okay, so this eventually gives us a 128 divided by 3. So this force here is 128 divided by 3 kilonewtons. Okay, because we are multiplying by area, so at the end of the day we'll just remain with kilonewtons. Okay, so that is the equivalent force. All right, that's the equivalent force. So now let's apply the summation of forces, equations of equilibrium rather. You can think of that in 3D. So because of symmetry, I should make mention of one thing. Because of symmetry, CZ is going to be equal to BZ, which is equal to, you can call it, you can introduce another letter D. These are the same because of the forces on the roller, they are the same. Okay, because of symmetry. All right, so if this is the case, then now let's start applying the equations of equilibrium. Let's say summation of forces in the x direction. In the x direction, when you look at x, we only have ax, and we expect it to be equal to 0 because we don't have loading in that direction. Summation of forces in the y, also we only have ax, we don't have any loading in that direction, hence we will not have any reaction force. What else? Then we have summation of forces in the z direction. Okay, of course here we do have, so we have minus 128 divided by 3, then we have plus az, then plus bz plus cz. But we said bz and cz are equal, therefore we can write this as 1 minus 128 divided by 3 plus az plus 2d. Okay, this is what we said, right? We just defined this. Remember, we said these are equal, so all we've done is just replace there. Okay, great. So let's take moments about the x-axis. We say summation of moments about the x-axis equal to 0. And using the right thumb rule, since we are dealing with 3D, we are going to have a negative moment due to the equivalent force. So we'll have 128 divided by 3 times the lever arm, which is 2.4. Okay, see, this will tend to cause this to rotate like that. Okay, that's a negative moment. It's going in the opposite direction of x. Okay, summation of moments about the x-axis. Then we have plus bz, and cz will cause a positive moment, so bz by 4 plus cz by 4. So if we replace again, we replace this d there. Remember we said We replace D there. We also do the same and replace D there and make D subject to the formula. Then what we are going to find is D is equal to 12.8 kilonewtons. All right. So we know that this 12.8 is equal to Bz is equal to Cz. And then if we found what D is, we can come to this equation here and replace the D. We replace the D there. Okay. And if we did so, then we'll find that the value of Az will be equal to 17.07 kilonewtons. Okay, so it's like we are done. So let's just write everything. So we have Ax, which is equal to Ay, which is equal to 0 kilonewtons. We have Az, which is equal to 17.07 kilonewtons. We have Bz, which is equal to Cz, which is equal to 12.8 kilonewtons. And then we have the equivalent force, Feq, which is equal to 128 divided by 3, which is equal to 42.67 kilonewtons. And this location, x, y, x bar, y bar is equal to 0.2.4 meters. So this is really about it. This is the summary of the final solution, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.